Hi, we're the PokéIdentifiers, and today we'll be showing you our convolutional neural network that classifies Pokemon by type. I'm Sam Kratsas.
I'm Kyle Cox.
I'm Connor.
You open up your phone's photos, scroll through, and see a search bar suggesting items like dog, car, or cat. This software works by using machine learning in a field called convolutional neural networks to detect these items. These CNN models work at finding features such as color, lines, shapes that make the software believe it has found a particular item. Our smartphones make this task seem like a breeze, but how hard is it to actually make a CNN model for corresponding sets of images? In this project, we'll be creating a CNN of our own and we'll be testing it on Pokemon. Our model will be trained to detect features such as the order and colors of pixels from an image of a Pokemon, and we'll use these findings to make a near precise guess about the type of this Pokemon. Staying true to Pokemon, though, our project has evolved many times over the course of this study, so you will see how our model's performance changes when used on a few different Pokemon image datasets.
What had to be done with the data processing was a long, tedious process. Based on the original .csv file and image set that we gained from Kaggle, we had to go through all 809 Pokemon data entries and make sure the type was what the Pokemon looked most like. For instance, some Pokemon have a type of water/ice. We had to iterate through each Pokemon and decide which singular type fit it best and had to do this for every single data entry. Our 18-way classification image set, though, faced difficulty due to the fact the population of each class was so small, and to combat this, we made two other image sets to run through our model. One is an image set with just two classes, bug/grass as class 1 and ground/rock/steel as class 2. Lastly, a 6-way classification image set with classes dark ghost, ground rock steel, grass bug, normal fighting fairy, water ice, and flying. These types were combined into these classes this way based on trends they seemed to share in their color and body design. For example, normal, fighting, and fairy all share lighter colors and humanoid appearances.
For our current model architecture, we continue to use Keras and TensorFlow to create a CNN such that it has three convolutional layers that consist of convolutions, activation functions, pooling layers, and dropout functions within each of these layers. These three layers extract out the features of the dataset and produce a result within the classifier layer. Furthermore, the classifier layer consists of a flatten function, dense with an activation function of ReLU, dropout functions, and another dense layer which fluctuates between 1 to 18, which is determined by the amount based on the number of Pokemon types that are being classified. This last dense layer is different based on the different datasets that are being run through the model which compare different Pokemon types. In total, the number of parameters that comes from these settings consists of 11,178,578 parameters. The reasoning for adding to the complexity in the architecture of the model consists of taking a look at similar models that classified images and taking the similar principles that were being used, such as combining each layer with pooling layers and dropout functions. In particular to the results, we've noticed that our current model is only slightly outperforming our baseline model in scenarios that compare on fewer types, and absolutely abysmal on comparing between all types. As one can see from the figure above, graphing the training curves, our model is making some significant progress past the baseline on test sets with fewer types. Though these are all small margins, our training accuracy is better than the random generated baseline's accuracy, and our validation accuracy is better than both of them. We believe that the cause of this could potentially come from not having a big enough dataset to train on, even for the smaller testing scenarios. For example, we are trying to compare our 809 images into 18 different classes for our main tests, which is the main contributor to having such a low accuracy rate in all of our tests so far with the model. Throughout this whole process, we found that having a bigger pool in the data samples helped significantly with training the model, as well as only comparing between two different types. Despite only having a 60% accuracy rating, we feel that our model came a long way based on not having a large enough pool of images to train on, as seen in our results.
Over the course of this study, we learned a lot about what works and what doesn't work when designing a machine learning model. This was largely due to the challenges that we faced. At one point, we'd like to really drive home that you should always try to have large class sizes for your model. As a general rule of thumb, it seems to be bigger the class size, the better. And as for great datasets we use for our in-class examples, I saw one recently at DataCamp that had a class size of 2,000, which is far more than our 800 total image set we worked with Pokemon. I hope you remember this if you ever work with machine learning again, This concludes our presentation. Thank you, and stay safe, and have a great summer.